we will continue the discussion on Boolean function minimization. Last day we introduced the concept of Carnot map, which is nothing but a graphical representation of the Boolean expression, and using this Carnot map how we can reduce the Boolean expression, we can minimize the Boolean function, we are discussing that. So, today we start that Carnot map simplifications. Now, first we imagine a two variable sum of minterms. See, this is one example, that here x and y are the two variables. Now, this is the Carnot map of this. Now, here see that the x, both of these minterms appear in the top row of a Carnot map, which means that they both contain the literal x dash, means the x dash y dash plus x dash y. Now, here say this is the left hand side, the variable is x, that means this one is denoted by x dash. So, the first row, for the first row the literal represents is x dash. Similarly, the first column the literal is y dash. So, for the first element of the first row represents x dash y dash. So, the minterms are, the first one is x dash y dash. Now, the second element of the first row is x dash y. Now, we consider the second row. So, the second row, for the second row the literal is x. So, this is x, y dash represents the first element of the second row, and similarly the second element of the second row is x y, where the second column is represents the y, the second row represents x. So, these are the four minterms, four minterms. Now, the first row is x dash y dash plus x dash y. So, this is my function. See, the function is the, say, f equal to x dash y dash plus x dash y. So, this is my function f. Now, if I take common that x dash, this is y dash plus y. Now, we know that y dash plus y equal to 1, means this is from the theorem. Then x dash dot 1, and that is x dash. So, the expression becomes x dash. So, the function was x dash y dash plus x dash y, and that becomes x dash. Now, if we see that from the Carnot map, how we can tell that this is x dash? See, for the first row the literal represents is x dash. Now, the function consists of two minterms, and that is the first element of the first row and the second element of the first row, and this is a 2 by 2 table. So, both the minterms of the first row exist in the function. So, if we see the both the elements, that means my function f equal to x dash y dash plus x dash y. This is the first row. Now, as it is the whole row, that means the other literals y, its complemented as well as uncomplemented literal both exist in the function c y dash and y. So, they will nullify and only x dash will be there. So, from the table I can easily, by seeing the thing, I can tell that it will be reduced to x dash. That means, if I take the first row, then as y y dash both exist in the function or the minterms of the function, then only x dash will be there. So, what we have received or what we have just now computed by applying the theorems and the postulates, that x dash y dash plus x dash y equal to x dash, we can easily get that thing from the Karnaugh map also. Now, we take another two variable examples. Say this is x dash y plus x y. So, again if we mark the thing, say again that first row is the literal x dash, first column is y dash. So, this is a, for two variable, this map is a 2 by 2 table or 2 by 2 map. Then the first element is x dash y dash. Obviously, the second element of the first row x dash y. So, this is my x dash y, and second element of the second row, this is x y. This is x y. So, if my function constitutes of these two terms x dash y and x y, that means my function f equal to x dash y plus x y, then from the table what it comes? See, now from the table that actually the two terms exist in the second column where the literal is y. So, this is my y, and these two mean term consists complemented as well as uncomplemented one. That means they will nullify. So, only y will be there in the f. So, it should be y. That means my f should be y from the table or from the K map, Karnaugh map. Now, see, if I apply my postulates and theorems, then if I take common, as y is common here, so this will be x dash plus x, and we know x dash plus x is nothing but 1. So, this will be y dot 1 equal to y. So, from the applying the theorems or postulates, we are also getting f equal to y, and here also from K map easily I can see that it is f equal to y. So, x dash y plus x y reduced to y. Now, what about that x dash y dash plus x dash y plus x y? Now, I take another example where that table consists of, this is again x and this is my y dash. Now, my function consists of f equal to x dash y plus x dash y dash plus x dash y plus x y. Now, what are the terms from the in the map where it will be? So, we have x dash y dash plus x dash y in the top row corresponding to x dash. So, this is corresponding to x dash. So, if I write this is my x dash y dash, this is my x dash y, and another term remains, that is xy. So, the another term is the second element of the second row, and that is xy. See, the second row corresponds to literal x and the second column corresponds to literal y. So, the second element of the second row will be xy. So, this will be my, now how it will be reduced? Say first from the table, if I reduce from the table, say first we see if it is from table. So, if it is from table, if I consider only the first row, so already we have seen the from the first row what will be the reduced function, it will be simply x dash, it will be simple x dash. Now, another variable is there, that is xy, that is xy. Now, x dash plus xy is nothing but x dash plus y from the theorem. Now, if from the theorems and postulates, if I take the x dash common, then it is y dash plus y plus xy. So, this is nothing but x dash, because y dash plus y is 1. So, this is x dash plus xy, and this is nothing but x dash plus y. So, simply by noticing the Carnot map, I can easily reduce the function. Now, we see the 3 variable Carnot map. Okay. See that x, y, z, the function is, see the function is of 3 variable, and we write in this way that this is the function f of 3 variable x, y, z. Now, as it is a 3 variable, so what will be the number of minterms? What will be the number of minterms? The minterms will be 2 to the power 3 equal to 8 minterms. So, already we have discussed this will be x dash, y dash, z dash, then x dash, y dash, z, like all 8 terms will be there, x, y, z. So, first thing, my table should contain, the Carnot map should contain 8 rooms or 8 elements. So, now I draw the map. Say the row represents only one variable x, and that is 0 and 1. Now, the column represents the two other variables y, z. Now, for 2 variables, there will be 4 possible, 2 square means 4 possible combinations, or what the y, z value can take. Y, z can be 0, 0, y can be 0, z can be 1. So, this is 0, 1, y can be 1, z can be 1, 1, 1, and y can be 1, z can be 0. So, in this order 0, 0, 0, 1, 1, 1, 1, 0, and this is the convention normally we take, and this is 0, 1. Now, if it is 0, 0, 0, I think we can remember our minterm table and the sum of minterm tables, where we have represented that if it is 0, 0, 0, if it is 0, 0, 0 x, y, z value, then we represent this thing as, this will be complemented one, x dash, y dash, z dash. So, as x is 0, this is x dash, or we can write also that this will be x dash, and this is actually x. Similarly, This 0 0 means this is y dash z dash, this is y dash z, because from the sum of min term tables we know that if it is the value is 0, that means it is a complemented one, and if it is 1, then it means it is a uncomplemented. So, y z and this is y z dash. Now, we take what will be the element. This is the first row when we are considering, that means x dash remains same. So, for the all the elements of the first row, that min term, in every min term x dash must be there. So, x dash, see the first element x dash will be there. Now, what the column is there, that I will add. So, that means for the first column y dash z dash, so it is x dash y dash z dash. Second column it is y dash z, so x dash y dash z. Third column it is y z, so it is x dash y z. Fourth column it is y z dash, so it is x dash y z dash. For the second row it is x. So, for the whole second row, all the elements of the second row, that the x literal must exist, and similarly it will be x y dash z dash, x y dash z, x y z, x y z dash. So, now if I remember the min term notation, so that means the first element is actually 0 0 0, means it is the m0. Similarly, it is 0 0 1 means m1, it is 0 1 1 means m3, it is 0 1 0 means m2. For the second row, it is 1 0 0 means 4, 1 0 1 means 5, 1 1 1 means m7, 1 1 0 means m6. So, this is my K-map picture. Now, with this ordering, so we have seen that there are some ordering there in the map. Any group of 2, 4 or 8 adjacent squares on the map contains common literals that can be factored out. See, if I consider, say this is my x dash, this is my x dash, and these are my, see here this is y common, this is y is common here, and here y dash is common. So, now see, that if I consider these middle two adjacent min terms, then it will be x dash y dash z, and it is x dash y z. So, see, for these actually z remains constant. That means for these two element, z remains constant. X dash constant and z is also constant. Whereas for these two element, that x dash y z and x dash y z dash, x dash remains constant and y remains constant. Similarly, the first two terms if I see, x dash is there because all are in first row and y dash remains same. So, that means what just now we mentioned, that with this group of 2, 4 or 8 adjacent squares, it must contains some common literals. So, for the first row, the common literal is x dash. And if I take a group, then if I mark this as the first element 1, this is my first element, say this is my 1, say this is my 2, 3 and 4, then what we can tell, for 1, 2, that means if I take these as a group 1, 2, then x dash is for all the elements, all the min terms x dash will be there, and then y dash will be there. Similarly, if it is 2, 3, then x dash is as it is there and z is there common. Similarly, for 3, 4 group, x dash and y is the common literal. Now see that if I take 1 and 4, if I take 1 and 4 as a group, means this 1 and this is 4, then x dash is as it is common and z dash is also common. So these are the some common min terms I am getting. So easily it can be factored. That means from the common, if common literals exist 2 min terms, then the common literals I can take out from both the min terms. So it can be factored. Now we see that how we can do this grouping. So keeping this thing in mind, that the adjacent, just now what we have seen, the adjacent 2 min terms always contains some common literal. That can be 1, that can be more than 1. So keeping this thing in mind, now we will group 2 or more than 2 min terms. How? So we call that adjacency because we are considering only the adjacent min terms. So adjacency includes wrapping around the left and right sides. Just this is one example. That means as if we are considering the extreme right hand side min terms, they are actually adjacent to the extreme left hand side min terms, means as if they are wrapped around. That though the table is kept as a flat thing, but if we fold this thing, if we fold the table in a cylindrical manner, then as if the left hand column, the rightmost column and the leftmost column, they are adjacent. So we can group them together or we can treat them as an adjacent one. So we will use this property of adjacent squares to do our simplifications. So say for this particular example, if I take these 4 as the adjacent groups, and we see whether the common, what are the common literals, or whether we can reduce that thing or not. That means say I have one function that x dash, y dash, z dash. The function consists of, so I have one function f that consists of x dash, y dash, z dash plus the last term means x dash, y, z dash plus the x y dash z dash plus x y z dash. See again that thing. So, this is x dash y dash z dash, x dash y z dash. Similarly, this is x y dash z dash, because for the second row x is the common literal and the last term will be x y z dash. Now, how we can reduce that thing? So, how we can reduce? See, first what we are seeing, in all the terms z dash is common. So, I take z dash common, then this is x dash y dash plus x dash y plus x y dash plus x y. Now, see whether I can reduce more. See, in the first two terms x dash is common. So, take common y dash plus y. The last two terms x is common. So, this is y dash plus y. Now, we know y dash plus y is 1. So, this becomes z dash x dash plus x. So, this becomes only z dash. See, so this 4 min terms reduces to z dash only. So, this 4 min terms reduces to only z dash. Now, what we can tell? That means, if we can group 4 adjacent cells, then it always reduces to only one variable if the function is a 3 variable function. Just now what we have seen. So, again we are taking some example of K-map simplification. So, this is again a 3 variable function and the function is xy plus y dash z plus xz. So, first we should convert the expression into a sum of min terms forms if it is not already. The easiest way to do this is to make a truth table for the function and then resolve the min terms. So, see how we can convert that thing. So, first we will form the truth table. See, this is the truth table for the function given. So, as this is a 3 variable function, so 2 to the power 3 or 8 combinations of variables are possible, all 0 0 0 to 1 1 1. Now, what will be the function? The function will be x dash y dash z. So, x dash y dash z, for x dash y dash z the value is 1. See, this is the function. The function is x dash y dash z. So, for x dash 0 0 1 it is 1. X y dash z means 1 0 1. See, 1 0 1, that means for M5 min term, that is 1. Then x y z dash means 1 1 0 6. So, M6 term is 1. 1 1 1 means M7. M7, that it is 1. So, that means in the truth table M1, M5, M6, M7 terms will be 1. Now, with this ordering, any group of 2, 4 or 8 adjacent squares on the map contains common literals that can be factored out. So, now as we know that for these min terms, that means just for this example M1, M5, M6, M7, this is 1, then what I will be doing, that now I can draw a Carnot map and I will put 1 for the min terms which exist in the function. And now we will form the adjacent, or we will select the adjacent 2, 4 or 8 such min terms. Now adjacency includes wrapping around the left and right sides. Already we have seen that when we are considering or when we are selecting the adjacent min terms, then we will consider the wrap around also, as if the table Carnot map can be folded, and so that the extreme leftmost column is adjacent to the extreme rightmost column. So we will use this property of adjacent squares to do our simplifications. Now we see how we are doing the ordering. See, I take one example of 3 variables. Okay. So I put the x dash literal here, and this is for yz terms. So okay, for this is y dash z dash, this is my 0 1 means y dash z, this is yz, and this is yz dash. Now see, if I take the 2 adjacent min terms in the first row, what are this? This is marked as this red line. So this is x dash y dash z plus x dash y z, these two. Now as they are adjacent, so there must be some common literal, already we have seen, and from here also we are seeing that the common literal is x dash z. So x dash z we take common and it will be y dash plus y dash plus y is 1, so this is x dash z. So that means these two, see, these two min terms are reduced to x dash z. Now already we have seen this example that if it is these 4 adjacent min terms, if I take that x dash y dash z dash, x dash y dash z, x dash x y dash z dash means the first column and the last column, and we will be seeing already we have seen it is minimized to z dash. So if it is a 3 variable function, the 2 adjacent min terms reduced to a min term contains 2 literals, and for a 3 variable function 4 adjacent min terms are reduced to a term which contains only 1 literal. So they are reducing in this way. Now we see that why do we need the unsimplifying expressions? Many times when we use the Carnot maps, we will need that thing. See, a sum of min terms with Boolean algebra, apply the distributive law in reverse to add. In the expression can be converted to missing variables. Sometimes that even it is a 3 variable function, but the function contains a min terms where 2 literal exist. So if the other literal does not exist, what does it mean? Okay, we see what does it mean. See what, say one function f, this is a a, b, c, the 3 variable function. Now, it consists say a b plus a bar c b. So, these two terms. Now, this what does it means a b? Because it is a 3 variable function, it means that one literal c that does not exist in the a b. So, I can easily introduce a b in such a way that c plus c bar, because a b means a b dot 1 and 1 I can always replace by c plus c bar, and the remaining thing is there, a dash c b. So, this actually becomes a b c plus a b c bar plus a bar c b. So, this is a sum of product forms are where all the min terms consist all the variables, and this is absolutely necessary when we are making the truth table, because in the truth table or in the Carnot map, which elements will be 1? That means, if I draw a Carnot map now, say we are drawing a Carnot map, say we are drawing a Carnot map. This is a 3 variable. So, this is a dash and this is my a and this is my b dash c dash, this is my b dash c, b c and b c dash. So, this is 0 0, 0 1, 1 1 and 1 0. So, that means ABC, see ABC exists, ABC means here this is 1 1, ABC dash. So, A B C dash means this is my ABC dash and A dash CB, as A dash is there, so it will be in the first row and CB means this, so this will be 1. So, that means if I can represent my function in this form, that means the sum of min terms, or what we have defined as a canonical forms, the sum of min terms forms where all the min term contains all the literals, then I can easily make my Carnot map like this. So, if I now take this example, so one example we take, that example is that xy plus y dash z plus xz. Now, how I can, this is a 3 variable function, this is a 3 variable function. So, if I want to make that thing that all the min terms should contains all the variables, then xy I can put xy dot 1. Similarly, y dash z is y dash z 1, xz dot 1. Now, that see here the first term z is missing, the literal z is missing. So, 1 I can replace z dash plus z. Similarly, in the second term x is missing. So, I can introduce x dash plus x as a 1, and here the 1 is replaced by y dash plus y, because that y literal was missing in the third term. Now, if I apply the distributive law, so what will happen? X y z dash, x y z, y dash z, x dash, y dash z, x, x z y dash, x z y. Now, from here all x y z, see there are 2 x y z, so it will be here. Then x y z dash, so x y z dash is here. Now, x dash y dash z, this is here, and x y z dash, there are 2 terms here, so they are mapped to, because x plus x is x, here x plus x is x. So, applying this rule, it is simplified to this. Actually, further we can do that simplification. We can do the further simplification here, that we can take xy from here, we can take the xy common, say xy then z dash plus z. Here we can take y dash z is common, then it can be x dash plus x. So, what will happen? This becomes xy plus y dash z. So, it is reduced to xy plus y dash z. So, the resulting expression is larger than the original one. Sometimes we are intentionally doing that thing. If some literal is absent in one min term, we are introducing that min term so that we can easily form our kernel map. But having all the individual min terms, making it easy to combine them together with the K-map, and this is the reason that why we are introducing the literals which are absent in one min term, and that is why the canonical form is very important. Now, the K-map example. Again, we are taking that 3 variable example. So, put ones in the map for each min term and zeros in the other squares. That means, if I take one function, say here the function is x dash y dash z plus x y z x y dash z x y z dash plus x y z. So, I will put 1 where these min terms exist. So, see that this is x dash. So, x dash and this is my y dash z dash, this is my y dash z, y dash z, this is my y z and this is my y z dash. So, x dash y dash z, x dash y dash z means this is the min term exist. X y dash z, x y dash z means this is another min term which exists in the function. X y z dash, see this is x y z dash, this min term exists, and x y z, this is the min term exist. So, I can put 1 for them. See, I have put this thing, I have put it that this is the 1, this is a 1, this one, there are 4 min terms and I have put it that thing there. So, already what we have seen, now if I can take the adjacent 2, that means, see these 2 are adjacent, these two are adjacent and these 2 are adjacent cells. Now, easily this can be reduced. We can see now itself, see for these 2, that what we can see that f is f equal to this is x dash y dash z plus x y dash z. See, this is the column for y dash z. So, only y dash z will come here. See, here only y dash z will come. If I take y dash z, this is x dash plus x and this becomes only y dash z. Now, but another 2 terms are there. So, now we see another 2 terms, this is the in the row x and this is x y z plus x, y, z dash. Now see, for these two terms the literal x is common and the y is common. This is yz and this is yz dash. So this is yz dash. So for these two mean terms, y is common and as they are in the second row, x is common. So if I take x, y common, then again this is z plus z dash. Z plus z dash is 0, so this becomes xy. So the function reduces to y dash z plus xy. So how we can make the group? How we can make the group? That grouping together all the ones in the K-map. Make rectangles around groups of 1, 2, 4 or 8 ones. So here there are only 2 groups I can make. Each consists of only 2 mean terms. All of the ones in the map should be included in at least one rectangle. So no one can be left during the grouping, and one can come in more than one group. So do not include any of the zeros. So this is the rule for my grouping the mean terms. Now each group corresponds to one product term for the simplest result. Already we have seen that for 3 variable, if we take or we can make a group of 2 mean terms, 2 adjacent mean terms, then it reduces to a mean term having 2 literals. For a 3 variable function, if we can make a group having 4 adjacent mean terms, then it always reduces to a mean term consisting of single literals. So each group in this way, each group corresponds to one product term for the simplest result. Make as few rectangles as possible to minimize the number of products in the final expression. So as the each group reduces to a mean term, so our aim will be first to reduce the number of groups. That means to reducing the number of groups means always we will try to select the largest group if possible. So we will find out or we will search for a largest group. So make each rectangle as large as possible to minimize the number of literals in each term. Already we have seen, if it is a group of 4 for 3 variable case, if it is a group of 4, then it is reducing to a single literal. If it is a group of 2, then it is reducing to a mean term, but it consists of 2 literal. So if the size of the group increases, then the reduction is more. So it is all right for rectangles to overlap if that makes them larger. That means that one can appear in more than 2 groups. Now each rectangle corresponds to one product term, and the product is determined by finding the common literals in that rectangle. And already we have seen by example that how the literals are common for one particular column or one particular row. Already we have seen that for say for again we are repeating that thing, that say for this column, so this is actually for this column y dash z. So for this column it always this will reduce to y dash z. Say for second row for this group obviously x will be there, and for these two which one will be common, because it is yz and it is yz dash, so that means y is common, so they reduce to xy. So already just know the one example we have seen that this type of function reduces to y dash z plus xy. So only by seeing the K-map and by grouping them, I can tell that if the function will reduce to this. Okay. Now reducing the expression of larger variables. This all today we have seen that for 2 variables and for 3 variables. Okay, this is the rule. Now if I summarize the rule that how we can reduce the expression, then in reducing the expression f to the simplest form, first look for adjacent locations containing 1. So I will draw the K-map. In the K-map, some of the elements are 1. Which elements are 1? The minterms which exist in the function, that particular minterms will be 1 in the K-map. So first I will look for adjacent one, then forms a couple if it is 2 adjacent one. This couple is defined as a box or as a group having 2 minterms, having 2 adjacent one. So couple is a group having 2 adjacent one. Similarly, quad is a group having 4 adjacent one. Octuplet contains 8 adjacent ones, and a hex box contains 16 adjacent ones. And always our aim is to find out the largest groups if possible, because it always achieves the maximum reduction. So this is the overall rule for the simplification of expression or reducing the Boolean expression using Karnaugh map. So again, if we apply the rule just now I mentioned, say for 2 variable it is AB plus A bar B, AB bar plus A bar B bar. So these are the Karnaugh map, and the mean terms exist is AB. So the mean term will be, this is my just now the first couple will be, see this will be, the term exists is A bar B bar. Okay, this will be A bar B bar. This is A bar and B bar. So the term that I can write the function, this is the function that z equal to A bar B bar plus A B bar plus this is my A B. Okay, the same example I can tell. So that I can, okay, AB plus A B bar plus A bar B bar. So that particular 3 elements will be 1. This is my AB, this is my A bar B bar, this is my A B bar. So what will be the first couple? First couple means 2 adjacent one. Now see here, if I plot that actually there will be 2 couple, this is one couple and this will be one couple. See here that this one, that means that AB bar, that is common in both the couple, but it takes a. So what will be the first couple? First couple will be A bar B bar plus A B bar, and if I take B bar common, this will be only B bar. And see, so actually the first column represents the B bar. First column represents the B bar. Similarly, it should be A. From the kernel map, the second couple should be reduced to A, and see, the second couple is A B bar plus A B. If I take A, then B bar plus B means 0. So this becomes A plus B bar. That means it is reduces to the literal for the second row A and the literal for the first column B bar. So it is reduced to A plus B bar. Now if it is for a 3 variable function, then simplify the Boolean function, this A bar B C, A bar B C bar, A B bar C bar, A B bar C. Now I have to draw the kernel map like that. This is A bar A, B bar C bar, B bar C, B C, B C bar. So the min terms exist A bar B C. So A bar B C means A bar B C. This is one min term. A bar B C bar, A bar B C bar. This is one other min term, and the rest min terms are this. Now see, if I take the couple, now if I want to form the couple, then this will be a couple and this will be a couple. So the first couple reduces to, what will be the first couple reduces to? First couple reduces to the first row A bar and B. See here these two term, B is common. So A bar B, see it will be A bar B, and the second couple A is common and B bar is common. So A B bar. So it reduces to A B bar. So from seeing the only noticing the kernel maps and making the groups of two or making the couple or this thing, I can easily do that thing. Okay, we will finish that here. We see that the quiz of this. So these are the 3 questions for the lecture 8 and 9 quiz. Just there are 3 simplifications using K-maps. The first one is x equal to AB plus AB bar plus C bar plus A bar B bar C bar. Second one is y equal to ABC plus A B bar C bar plus A B bar A B C bar plus A bar B C bar. And third one is A B bar C bar plus C bar B plus ABC. Again we will continue this thing in the next class. Thank you.